please, any of the volunteers or staff in the black t-shirts will be able to help you out. Okay, so I think we're now ready to actually start. Yeah, okay. Welcome to the 7th Data Science Festival, being held here again in CodeNode. I know many of you have been before, many of you have presented. Welcome to those of you who've not been before. It's a really engaging day, and I hope you make lots of links within the data science community. Data Science Festival is really aimed at building that community. So we're looking to engage people on techniques, but also collaborations, and obviously some people are looking for jobs. We can only do this thanks to the help of our sponsors. This year that's BSI, Digitas, Data Idols, Compare the Market, Unidays, Time Extender, PwC, King, Clio, Product Madness, dunnhumby, and Create, and obviously CodeNode helping us out with great AV support and facilities support, to which we're really grateful. LinkedIn are also helping this year. There's a tag competition. If you can put your favorite part of the day onto LinkedIn, tag it with hashtag DSF Mayday, and tag @Data Science Festival, you're in with a chance to win a hamper, £100 Amazon voucher, some books, DSF Bluetooth speaker, and other goodies. So, I'd also like to point out that Data Science Festival is about community. It's about supporting those with less opportunity to get into data science. One of our key community partners is UN Women, who are building a global community sharing a vision of an equal and diverse society. One of their initiatives is the He for She campaign, which is an invitation for men and people of all genders to stand in solidarity with women to create a bold, visible, and united force for gender equality. If you're interested, you'd like to contribute or donate, you can find more details at the back of your program booklet today. So, without more ado, time to move on to our first speaker. Daniel Svonava from Superlinked is the CEO for a company that's making an infrastructure product that makes it easier to build engaging and safe software platforms. Previously, Daniel was a tech lead at YouTube, where he built modeling for user engagement and ad performance, which helped build the YouTube ad sales up to $10 billion a year. So if I can invite Daniel to come up.
Thank you very much. Does this work? Yes. Yes, very good. All right, so thanks to all of you for waking up so early. This is the first talk. Let's do this. Maybe quick show of hands in terms of who heard about vector embeddings before. Very good. Expert audience. Cool, so you heard a few words about me, my background. So let's just dive right in. I would like to discuss how to, do the technical aspect of using vector embeddings, but then also how to actually use them in your products to make them better. It's all about that application. Cool. So today I want to cover why vector embeddings are useful representations of your data. Maybe use a metaphor you haven't seen yet, because people struggle to explain these data structures. And then we'll look at what you can build with vector embeddings, and what the previous approaches were to those same problems, and where they maybe come up short, and how vector embeddings save that or fix that. And then we'll talk about how to actually go from the early experiments to building MVPs, and finally how to do this properly, right? So let's just start. So first of all, let's build some intuition about vector embeddings. And I think we should start in kind of the data we want to model. So usually, your users, the data out there in the world is rich, right? It has fine gradations, fine differences. And for example, we can capture this with a photo, right? And the Windows fans out there might recognize this one. So, to capture something like this, we need 1 million pixels, let's say, with their RGB values. So it's kind of like a book worth of information, right? And sort of like all the data that matters kind of looks like this. But like we're humans and we simplify things, right? And so we invented language, for example, or other structured data, which aims to simplify what we see out there, right? So we can just say, okay, this field of grass, 3 words, super simple. But then, when you have structured data, you are compressing the information, right? And so field of grass can also mean this. I actually use Mid-Journey to generate an image from the same text, right? And it's sort of a field of grass, but it's a very different picture, right? And so the language here, the structured representation of this data is ambiguous and imperfect. So what we do in the structured data world, we refine from there, right? So we say field of grass on a summer day, right? We add some more. And it's closer to where we started, but it's still a completely different place, right? And so you can kind of keep doing that, right? You can kind of add more structured data to describe what is the actual item you are talking about. Let's say your user with all their sort of complexities. You can add more structured data to describe them, but it's always going to be imperfect, right? And this is because we have this bottleneck in there, right? So with some sort of explanation, we got to something that's reasonably in the ballpark, but we lack the gradation, right? We lack the fine differences. And so this is what makes structured data not such a useful representation if you want to, for example, train a machine learning model, right? Because machine learning is basically an exploration of some sort of space. And if your space doesn't have a way to capture those fine differences between data objects, the model will struggle to understand it. And so, okay, here come vector embeddings, right? Just think of a function that takes any sort of object on the input and produces a set of coordinates in some space, right? And then the problem is about how do you construct the space so that it's useful for your problem, right? And we can see that, for example, if we train the model to better distinguish fields of grass, it would help us navigate that by sort of putting the coordinates that represent sort of more green pictures here, and then the yellow there, and it would be able to capture also anything in between, right? So basically, imagine like a smooth space that transitions from this Windows background to all the neighboring points. And this is what kind of returns the richness into our data representations, right? We went from the real world that is, infinitely complex to structured data over the last 20 years when we, have our databases and all that. And we lost the fine resolution, and now we are getting it back because we are representing stuff with vectors. So that's good. Now, before we did this, how did we approach certain problems which vectors now can help us with? And I'll basically go into information retrieval here, right? There is a quick kind of detour into generative AI at the end, because somehow generative AI drives the hype around vector databases, and it helps us, it helps the vector databases get the funding, and then we can use them for the important problem of information retrieval, right? So just to kind of catch us up, search before vectors, was all about keywords. Here is an example. I chose, an online pharmacy, but it's a big company. They have invested, 2 decades of work into search. But if you do it based on keywords, then if you search for splitting headache, you'll get 1 essential oil back and no migraine pills because it's just different keyword, right? And so the world of search is a lot about just tweaking these manual rules, expanding those keywords, having your sort of NLP pipeline in there that does synonyms, and then a big full text index. And you are fine-tuning this every time you realize, oh, this query also doesn't work. Okay, so it's an unsolved problem, search, right? And then the other side of search is recommendations. Currently, all the different use cases you can imagine online, marketplaces, content platforms, social networks, all of that is driven by recommendations, right? So this is arguably a more important problem than search even. And we also, historically, the experience out there is not awesome, right? Here is a screenshot from LinkedIn that keeps recommending me intern jobs. And that does little for my confidence, but then also if I kind of, I just try to understand where this is coming from. And it's coming from the fact that your typical recommender engine stack has usually these two steps in it, right? You do the candidate retrieval. So basically, you have your jobs in this case in a big database, annotated with some metadata, right? And before you recommend, the top 3 jobs for a user, you do some crude search on this database, right? You kind of filter based on some parameters to generate candidates. So let's say you generate 10,000 jobs that Daniel could be interested in. Somehow the intern job gets in there. And then you have the ranking step, right, which is a separate model that for each of those 10,000 items calculates the probability that Daniel will be interested in this job or that job or that job. And that takes a while to transmit all the data, right, from the retrieval to the ranking. And then you need to score each of them, call the model, finally sort by the resulting probability, and return the recommendation, and it's still kind of wrong. And the problem is that this, you generate the candidates in a very crude way, and there might be all kinds of other jobs out there that you didn't find, and so the ranking then has no knowledge of them and then can't recommend them, right? So this is, it's kind of a bypass of the problem that we can't look at all the jobs in the index and find, navigate the trade-off of what seniority is the job, what Daniel preference might be, navigate all of those trade-offs and do that in the index so we can retrieve not 10,000 rough candidates, but 10 pretty good jobs, right? And this is what the vectors help us do, basically. So when you talk about implementing this type of stuff with a vector index, we mean that basically we are using a database that for a given coordinate point, right, for a given vector, can return very quickly a set of neighbors, right, in the space that we have constructed. And there has been a lot of development in the infrastructure providers for these indices, and we need to figure out the way to use that technology, right, to kind of get better at this because the experience still sucks. Then what are we putting in that index? We are putting there the representations of our content, right, because we want to surface some information to people, but we are also putting there the vectors that represent our users, right? This is the slightly weird idea, right? Because typically you just had a database of content and then you try to search into it. But I argue that it's useful to also keep track of each of your user vectors, save that, and then use it for information retrieval or finding similar users or solving all kinds of other tasks that I'll touch on. And then finally, if you do a better job in the retrieval step, you don't have to do the ranking on top as much, right? You can just sort of verify some assumptions. You can do maybe light filtering, but basically all the heavy lifting is done in the index. Just a quick word about approximate nearest neighbors. So this is the family of algorithms that allows us to pull this off. So when there are two words that are worth discussing. So we have the nearest, right? What does it mean to have the nearest point? And this depends on the model that produces the vectors, of course. But for example, we can say that we don't care about the length of those vectors. So we want this kind of scale independent, and we just care about the angle between them. So maybe we do some sort of cosine similarity type metric. And then fast, just to give you an idea of sort of in practice what I mean, you can do on a single machine thousands of queries per second in basically a database of tens of thousands or maybe hundreds of thousands of vectors, sort of 1,000 dimension each, right? So this is the new thing. Like you can have 1,000 dimensions that create this fine-grained representation, and then you can retrieve them very fast. Cool. So let's zoom in a little bit more into how we create these vectors. Basically, first let's start on the content side, right? The idea here, right? And like the components here are not new, right? In your previous generation information retrieval system, you would take into account, a topical summary of the content, some sort of collaborative filtering or popularity-based signal, content quality recency. You would take all these as features into your ranking model. But what I'm saying here is let's concatenate all these things into one big vector, and let's let the vector retrieval, the vector index, do the work of balancing between those objectives, basically, right? So in this case, let's if we take an example of a social network and the feed, the personalized feed of content, the users would care about kind of topically interesting content and potentially popular content, and they would have some threshold on quality that they care about, how sensitive they are to that, and then also how fresh the content should be for them to like it, right? So we extract all these things on the content side, and we maintain a vector in our index that captures that information. And then, as I said, we do the same thing on the user side, right? So basically, imagine that both the users and the content are embedded in the same space, but the actual values represent kind of the opposite thing, right? Like the counterpart aspect of it. So basically, for the topical part of the vector space of first, let's say, 500 dimensions, right? For the content, this would be some semantic embedding representation of the content. For the user, it would be an aggregation of the semantic embedding of the content the user liked before, for example, right? So it would be an aggregation of the preference topically that the user has demonstrated through their behavior, right? So this is the same space, same semantic embedding space. It's just on the user side is the preference, and on the content side is the description of the content. And this you can do for each of those kind of hyper dimensions, right? You can you can express, the collaborative filtering signals. This user is similar to this other user on the user side, and then you can do, a representation of which type of user likes the content on the content side. And once you have that, a quick aside, this works because when we do some sort of cosine similarity, we kind of go dimension by dimension, right? We multiply the first two numbers, multiply the second two, and add it together, right? Which means that, like, if we have this vector, the topical preference gets kind of treated independently. The popularity preference gets treated independently because each dimension is just multiplied with itself, and then you just add the whole thing up, right? And so this allows you to kind of do this concatenation into one vector. Obviously, you can do weights, you can do all kinds of stuff. And in the end, just think about something like this, right? Imagine a space that has basically those three hyperdimensions, right? Those three clusters of coordinates. In this case, it would be relevance, popularity, and freshness. And then all your users and content are points in that space, right? So you might have seen, these demos where they ran content through a semantic embedding, like a sentence bird or some sort of model like that. And then, okay, similar content is clustered together, like with the pictures of the grassy field. Expand that in your mind into kind of more dimensions that also capture other stuff about the content, for example, freshness. And then, the user that's near the content, this is not just about the fact that user likes cat videos, and this is a cat video, but also that the user likes fresh content, and that's a fresh cat video, right? So, you can kind of bundle all of that into the distance by constructing the right space. Okay, and then very quickly, there is just sort of a manager on top of the vector index that allows you to do all kinds of different things. For example, you can take the user vector that compresses the user preference, the user history, and you can override the relevance part of it with a search query, right? So the user not only has some history and wants a recommendation, but also now they are searching for something, like a splitting headache or whatever. You can embed that query with the semantic embedding and insert it into the relevance preference part of the user's vector. And then search with this, right? So now it's personalized search, right? Because you also still express, the desire for recency or popularity into the same vector, and now you also, so like the search extension for this is relatively straightforward once you have all that other stuff. And then you can do, other sort of assertions, or you can do multiple queries and merge them to go for diversity. I'll not go into like all these options here, but basically the main idea is it can be simple because the index is doing the heavy lifting. All right, so in terms of practicality, you'll see, I think this sort of implementation of these ideas you can find online, example Python notebooks, super easy. So you just need your content, you need a Python notebook. You need a vector embedding model from Hugging Face, or you can just use OpenAI API that will return to you a vector for your data. And then just some sort of cosine similarity distance metric, which is not going to create an index, is going to kind of create distance for each content from each other, for example, and then you can do the plot I did with the pictures. So this is a good way to start experimenting. By the way, each of my slides has a link, and maybe the slides will be available afterwards, so that could be helpful. Then in terms of, OK, so you have built your Python notebook, you have experimented, you got some idea for how these embeddings work. To have a user-facing product, I suggest to add 2 components. So you want the vector database is the place where you'll store your vectors, is the place where you'll look them up when the user wants to search or have a recommendation. And then I suggest to really focus on evaluation, right? Because at the end of the day, like there already is search and recommendation infrastructure and solutions out there, and it only makes sense to bother with sort of new technology if it actually works better, right? And so you have to figure out if that's the case, and what do you need to kind of make it work better. And so, yeah, there are different approaches to evaluation, but ultimately, I think it's about, do the people apply for more jobs? Or do the people study more classes because you recommend them the right ones, right? I think this is kind of ultimately the objective that you have when you try to improve your information retrieval is, are the people that use your software actually achieving their goal more often? Okay, and then finally, all right, so you have built your MVP, and you managed to prove some initial value quickly, which for every data scientist knows that you need to sort of do that fast, otherwise the project might go away. So you have done that, and now it's time to kind of switch on the engineering part of your mind, right, and kind of do this in an organized way. And we have been at Superlinked playing with setting this up as an infrastructure product for a few different companies already, and this is kind of the model that we think that works. So you need, basically, you have all your inputs, right? Your content, your user, and your events data, right? So this is analytics, what are the users doing, right? The events. And then, obviously, you need some sort of API server. But then, basically, you do the transformations, right? So you pull out from the data both from the structured and the unstructured parts. You pull out the information that you want to feed into the embedding models, which you do here, right? And here, it's kind of a combination of, OK, I load an embedding model from Hugging Face, but then also maybe I have to vectorize my recency, right? And I want to do it without baking the age of content into the vector and then going back to the database and updating that every day. Not good, right? And so I need to figure out a way how to deal with recency in this kind of linear algebra paradigm. So that's, every time you add a new dimension there, you might have sort of a little research project going. That's why, for example, we have kind of a set of basically vectorizer templates for kind of the usual data types. So that's how we deal with it. And then you have your retrieval based on the nearest neighbor lookup, vector database under the hood. There is a lot of them, all kinds of benchmarks now available. And finally, you kind of have another API that drives all the different use cases, right? I kind of talked about the recommendations and search, but bot detection is another use case for when you are able to tell which of your 2 users are most similar to each other, right? If one of them gets flagged as a bot or some sort of like user with behavior you don't want on your platform, then maybe review the user that's the nearest, right? Because they have done similar stuff. So yeah, you can do segmentation, all kinds of stuff. But as a basis, you have your vector database with real-time updated user vectors and content vectors. OK, 3 quick lessons from doing this in different contexts. So we have been working with a social platform, and there the learning has been, and that was all about the personalized feed there. And you would think that basically the product manager or the product owner of the platform has an objective, some sort of metric they want to optimize, like for example retention. And then that will be sort of the sole guiding principle, right? But actually, in practice, the product owners have ideas they want to sort of use to guide the system, right? So they want to have some editorial control over this. For example, they want to promote more recent content because they brand the whole platform as more of a news-leaning thing, right? Rather than building up a catalog with historical content. So there is this need to balance between optimizing kind of black box metric. Back at YouTube, for example, there was a long period of time where all the systems were optimizing for views, right? Generating more views for videos, and that backfired because the thumbnails and video names got super clickbaity. And then there was a switch to watch time, right? More watch time means, okay, people click on the video and they actually watch it, so that's better. But every time you kind of just have one KPI and kind of blinders on, something will go wrong, right? So you need this way to reconcile these multiple dimensions together and have explainability, all that stuff. On the jobs marketplace side, this is a very kind of old school industry in certain ways. And there, basically, it's all about these kind of black and white Boolean filters. But actually, the user preference is better expressed as a trade-off, right? It's like, how far is the job versus how interesting is the job versus, does it match my career progression? These are not black and white constraints, but a trade-off, right, that I'm trying to navigate. So if I can express these different aspects as the vector parts, then the lookup basically blends between them, right? And it helps the user navigate the trade-off. So that's cool. And then in e-commerce, historically, e-commerce has been about third-party cookies, retargeting, A/B testing in terms of segmentation of traffic, because it's all sort of signed out anonymous traffic. But because of the privacy regulation, e-commerce is moving to first-party data, getting all the users signed in, which means there is a bunch of user history that just sits there and waits to be understood so that you can serve the users better. So e-commerce has been a bit of a sort of surprise for me personally, because that's not sort of my main background. But there is a bunch of data now because of the privacy regulation that is waiting for a data scientist to have a look at. All right, and finally, generative AI. You must be sick of this by now. But I want to, I want to just connect what we talked about, information retrieval, to generative AI. Like, what's the link here? And yeah, basically, large language models take text on input and produce text on the output, and they are stateless, right? There is nothing in the box in the middle that changes when you do this, right? So there is no internal memory of any sort. And then, people figured out that, okay, you can kind of take the output, feed it back in, let's see what happens, maybe do it in a loop. And the thing is that, so as I said, the model doesn't have memory, right? So it just takes the input, produces the output. If you kind of keep feeding the output back in, you can kind of simulate a chat experience, right? Because it will see its previous responses to you, it will see your responses to it, and so it can generate the next sort of reasonable response to all that. And nevertheless, it can fake a game of guessing a number, right? So basically, you just ask it, hey, think of number between 1 and 10. Don't tell me, just tell me if I'm too high or too low with my guesses. You can totally play this game with the machine that actually has nowhere to store the secret number, right? And it looks like it does, right? So that's but it's clearly fake. So that's interesting. And so, okay, so I obviously set this up in a way that it's the memory that the model misses, and it's the memory that you can give it by letting it come up with these vector representations for data, right? This is typically, there is some agent on top that controls this, and the agent decides, okay, am I going to generate a bunch of text, or am I going to generate a vector, right, that represents let's say, each paragraph of a book, and then maybe I'm going to store that in a vector database. So each paragraph will be indexed by its embedding vector, so that later on, when I need to summarize the book, or I need to cluster the paragraphs, or whatever it is, I'll do the lookup there, right? So it's basically a way to give large language model-based generative AIs state or memory. Cool. So yeah, that's a little bit of talk about the vectors and vector embeddings. Hopefully, you heard at least something new in that. And yeah, we are thinking about kind of this idea of vector ops, which for us, there is a gap between what the vector databases offer in terms of functionality. You can store vectors, you can look them up. But we talked about all this other work of creating the right vectors, the right space, managing all that, the complicated diagram of infrastructure. And we see there an opportunity for all kinds of different solutions that people will probably build in-house first. But the same way that MLOps kind of crystallized around some ideas, I think there will be some crystallization of this around building applications powered by vector embeddings. And this is kind of what I always nerd out on my LinkedIn about. So if you give me a connection, I would be very happy. Thank you very much.
Thanks, Daniel, for a really great talk. We've got some time for some questions, so would anyone like to start? If I just give you the mic.
Hi, thank you very much. That was really insightful. I definitely learned something there. Thank you. I had a question about the usage of user vectors. So do you envision there to be some sort of global user vector, or do you think that this would be that user vectors would be applicable to different industries? So you could say you have a user vector for like your job preferences, or you have a user vector for your free time or so, or would you think that there could be a global user vector that's applicable to lots of different kinds of recommender engines?
Yeah, so maybe we can split this question between kind of what's going on in one single company, let's say, and then there is also kind of the user side of this, right? Like it would be kind of cool to accumulate this vector and carry it around as a user and plug it to the new place, and now sort of it doesn't give me intern jobs maybe, right? So yeah, I think that you can, this kind of multi-objective idea, right, that you stuff quite a lot of the information into the vector and then you feed it into, do the retrieval directly like I described, but also feed it as a feature vector to other models. I think that also works. And I think the idea here is that if you can do it properly once, then your user vectors will kind of capture a lot of information, and there will be a lot of work that goes into that. And then all your kind of downstream tasks from there can be much simpler models, right? Much kind of straightforward process as well. So I think, and also you'll have consistency between the different use cases, right? So like when I'm searching versus when I'm getting a recommendation versus when I'm getting an email, like here's something you missed or whatever. Like ideally these are consistent with each other. And one step towards that is to use the same user vector as an input to all those different kind of sub-problems. So yeah, I think it's a good idea to try to generalize. Yeah.
That's great, thank you.
Okay.
Thanks, Daniel. Great talk. Just a question on clustering in the vector space. I think one of your slides mentions an ANN approach. I just wondered if you could expand on that. Kind of, do you think a neural network approach is best, or are there classical algorithms that also work quite well in clustering in the vector space? Cheers.
So this depends on the task, right? So what are you trying to achieve with the clusters, right? Do you have, let's say, a fixed cluster count you want to extract, or do you want to, do more of an unsupervised approach where maybe you do some sort of hierarchical clustering? I'm not so opinionated about the specific clustering algorithm, but what I think is that this kind of mindset of, okay, we have all the users, we'll cluster everything to kind of do that in a batch setting, right? Because clustering is kind of a global optimization problem, right? So you do the clustering, and then you feed it into whatever downstream problem you have. I'm much more a fan of just for a given user that you are trying to do something with right now, get the nearest neighbors, and that's kind of like their personal cluster, right? It's their little neighborhood, and then feed that somewhere else. Because this way, everything can be real time, and that's kind of an important aspect of this. I think it really matters to have those user vectors to be as fresh as possible. So ideally, the whole update takes you kind of sub-second, because that is what it takes to kind of get an observation. Okay, the user, kind of double-clicked on this job. That's interesting. And then already on that same page, you are showing like related jobs, right? Or other sort of other recommendations. You ideally use the last click as a part of the signal for that, which means it has to make it into the user vector. And like during the YouTube times, there was maybe like 30% of the signal comes from the last click. So if you don't have that, you miss out a lot, right? And so global clustering, I think it's kind of a step towards more of a batch computation and kind of something you can do kind of nightly to establish some sort of baseline. But then when it comes time to actually deal with the user in an interactive way, just go do the nearest neighbor for that one user.
Okay, I think we've got time for a couple more questions.
Thanks for the great talk. I'm quite interested in how we think about like transparency and explainability in this space. Like, how do we go from like, oh, hey, we're recommending this job because it's similar to ones you liked, versus because it's near you and because you like jobs in this space and we think this is your level of seniority?
Yeah, that's a great question. If you keep the hyperdimensions, so like these 4, for example, separate, because you could make an argument of transforming this vector to a lower dimensional space to speed up the lookup, but then you are kind of mushing everything together, right? You are kind of compressing further. And then the explainability is a problem because the individual dimensions in these vectors are kind of meaningless for the end user. And so if you kind of enforce some order onto this, right, you kind of say, all right, like, I don't care sort of like what's going on here on this level and it's not explainable and like, that's fine. But I care that these 4 dimensions stay sort of demarked and kind of known that, okay, these signals are from that. Then basically you can attribute, right? So the lookup score, the distance score you have can be broken into, because the dot product is kind of independent. So you can break the contribution of that into the different parts and then report to the user, use that for kind of validation tests, get more insight, and also do tuning, right? So imagine that you can now train a model that has 4 parameters per user, right? Because it's basically balancing weights between 4 different properties, and now you need like way less user data to do that, right? And yeah, still maintain the explainability. So yeah, that's a good one.
Hi, thank you very much. Great talk. I'm not so familiar with the tools that are used for embedding nowadays. So maybe I missed the part where you said like it's very quick to look up in these like hundreds of millions of vectors with tens of thousands of dimensions. Which tools make it the search for the nearest neighbors so fast? Like what type of I don't know tools we have there?
So there is maybe let's split this into kind of the algorithms that manage to do that. And I would say maybe not tens of thousands of dimensions. That's like a bit of a stretch. I would say maybe low thousands is okay. And then, yeah, like tens of thousands, hundreds of thousands per node. And then you can kind of shard from there. So in terms of the services out there, there is now even a podcast about vector databases. So you can kind of listen to how people think about the problem there. There is ANN Benchmarks, which is a website that benchmarks all the vector databases. And there the interesting aspect is kind of the recall, right? Because it's an approximate search. So all the algorithms are approximate nearest neighbor algorithms. They partition the space in some way. They construct the graph, for example, like a nearest neighbor graph, and then do a traversal of that. So there are different approaches of doing that, but it's all approximations. And you can kind of tune the recall latency trade-off to kind of your problem. But typically, this kind of throughput I discussed was at around 90% recall. So from like the actual 100 nearest neighbors, you'll have 90% of them there, which in these use cases is totally fine because it's all kind of fuzzy anyway. So yeah, if that makes sense. And I think there is maybe like 10 different pinecone, quadrant, Redis. We use Redis, for example. Because we care about not only the lookup speed, but also the write speed. Because as I said, the real-timeness, I think it's super important. And so when you kind of update your vector, if the index takes a long time to rebuild, you'll not be using the last click into the next recommendation. So we use Redis, but yeah, I think there is like a bunch of different solutions that you can just Google.
Okay, I think we've got time for one more question if anyone's got one.
Thank you. Thank you, Daniel. I had a question about what happens if you're looking at a use case where the content itself changes. Do you run? Would you run a regular script that goes through the database and checks for changed vectors, or handle it on an ad hoc basis?
So the changes in our kind of mental model are events. And so basically, there is either like a database change event or a user click event or some sort of change happening. And we have an API where we push that, and then we have a real-time kind of pipeline that takes that new data point, vectorizes that, and updates the vector. So it would sort of load the old version of the vector, and let's say there is some sort of counter dimension, it would update the dimension, store it back in, and kind of do it per event, per change, per event. So like it's also useful to see if, for example, the vector database you are choosing allows for partial updates, right? If you have a vector with 2,000 dimensions, it's nice to be able to change one number without kind of rewriting the whole 2,000 numbers. But yeah, it's pretty fast usually, yeah.
Okay. Let's thank Daniel once again for a really great talk. So we're just going to switch over to our next speaker for a couple of minutes.
Yeah, and please find me if you have any more questions. I'll be around for the whole day.